Okay, for a given field extension L over K of field extension, and X an element of L, when we say L is algebraic whole over K. Okay, so notion of algebraic elements. And then if X is algebraic, I think we have already discussed in last TA sessions, but when X is algebraic, this, which is isomorphic to K polynomial ring modulo this irreducible polynomial, monic polynomial, and this is field. This is field. Okay, so in the last TS session, I think I have discussed that this is isomorphic. Yes. And what is degree of extension? This is just degree of mu, right? Mu
Yes.
xk. Okay. So after this, little bit about group theory was given when, I mean, when G is finite subgroup of K star, it comes as a corollary. G a finite subgroup. It is cyclic. Okay. In fact, it is true in any integral domain where we take, in an integral domain, any finite subgroup of multiplicative group of units, this is cyclic. G is cyclic. And then Lagrange theorem, which is basic, you might have already seen about Lagrange theorem. In fact, I should mention it. Any order of any element G divides order of G, where this small g belongs to capital G. Okay. Okay, so let's discuss about problems we are given. So the first problem is about finite multiplicative abelian group of order n, where this mu x, let me maximize it. Mu of G is just product of elements from this group G. Okay. In fact, mu you can define for any subset of G, just multiplication of the elements of that set. Okay.
Is it all elements?
Yes, here we are taking all elements.
Okay.
Repeating only once, okay? Because you have to take care here or somewhere here. Here we are not taking all elements of G, but we'll see. Okay, what is G2? G2 is just elements of other than identity. Every element is of order 2, right?
Yes.
G2 is identity union self inverses. What are self inverses? Elements from G such that they are inverse of themselves, means G square is equal to identity. This is called subset of self inverses. Oh, sorry, this also contains E, okay, because E satisfies this. But I can write here order of G is 2. These are elements which are self inverses.
Can I ask
this
a
is
question?
nothing. Yes.
Is mu G going to be only the elements of which are self-inverse of each other, or the product of the elements which are self-inverse of each other? Because all the elements which have other inverses are going to get multiplied because it's an abelian group. So that is going to be 1.
They will be cancelled with each other. Yes. So this is our first part of the question. We will say this. Okay.
Okay.
Okay. So and the this is called G2. And next is 2G. 2G is just elements of G which are squares. Okay.
Okay.
I just said this is nothing but a set of squares. Okay. For example, here if you see if your G is this -1 and 1, then what is 2G? This is just 1, because 1 is a square of 1 itself, and it is also a square of -1. So if you want to write twice 1, I just said this is nothing but singleton 1. Okay.
Yes.
So note it down. So now we solve first part problem, where we have to show that G2 and 2G both are subgroups of G. Do you see it? It is why it is subgroup G2?
Because it's abelian.
G2 is subgroup of G. What we need to check, first of all, E belongs to G2,
Yes.
because E square is just E, which is 1 here. So E belongs to G2, correct. What about X into Y or X into Y inverse? X and Y, we will take X into X and Y inside G2, and we have to show X, Y inverse. The question mark is here. Is this belongs to G2? What is property being in G2? X square is just 1, as well as Y square is also 1, right? Now we have to show if it belongs to G2 or not. So we have to show X, Y inverse square, this is 1 or not? Question mark is here, right? If it is 1, then X, Y inverse will belongs to G2 and G2 will be subgroup, right?
Yes.
Okay. So because this is commutative group or abelian group, this product can be written as X square into Y inverse square, right? Now X square is anyway 1. What left is Y inverse square, and this is nothing but Y square of inverse, and Y square is just 1. 1 inverse is 1. Okay. So I hope you understood this part from here to here. I can explain here. When you have Y inverse is equal to 1, if you square both sides, because it is commutative, this can be written Y square into Y inverse square is equal to 1, right?
Yes.
So Y inverse square is same as Y square inverse. Okay, this follows from here.
Is
Okay,
that not
so
true when it is not commutative?
that might not be, but I'm not sure. We have to check for that. But it is commutative, so we are very sure that it will happen.
Okay.
Okay, so let's see next part. We'll come back to this if we will have extra time. Okay. So G2 is a subgroup of G. What about 2G? E belongs to this because E is nothing but E square. So E is a square of something. So all squares of G, they are in 2G. So this implies E belongs to 2G. Okay. So now we have to show that if X and Y, these two belongs to 2G, will X, Y inverse belongs to 2G? Can you give some hint? Because X, Y both belongs to 2G. X
So
is of
x
the
is the
form,
square of some element and y is also the square of some element. So y inverse will be the square of the inverse of that element. And
correct?
it's a commutative group. So
So x y in this x y inverse, this will be nothing but a square b square inverse, right? And this is nothing but a
Yes.
square into b inverse square, as we have shown above from here. Now this is nothing but a square, sorry, a into b inverse whole square, right? Understood? Okay,
Yes.
because a is sorry, g is commutative group, g is abelian. So this implies that x y inverse, this belongs to 2g. This is x y inverse is in square of something, so it belongs to 2g. Okay, so we have shown first part of the first question, and in the second part we have to show that mu g is same as mu of g2. Okay, so we have to show mu of g is same as mu of g2. Here you were talking about, here it comes. What is mu g? Mu g is product of all, uh, let g is nothing but g1, g2, gn. Because it is finite, we can take like this. Some will be 1. Let's say g1 is 1. So this is nothing but product of gi's, right? All gi's belonging to g. Now, if you see the elements which are not self-inverses, means they have inverse other than themselves. That is not g. Okay, this product can be factored into two products, gi's, where gi square is equal to 1 into product of those gi's where gi square is not equal to 1. Okay, so in
Yes.
the second product from here, this will be equal to 1. Do you see why? Since gi inverse is not equal to gi, so gi into gj for some j, this is equal to 1. So they will cancel out with each other, some j not equal to I in the same bracket, because gj is also not satisfying gj square is equal to 1. Okay, so this is just
Yes.
1, what left is just mu of g2, this. Okay, so we have shown these two, this is equal to this one. Okay, so we see the next part of the question. If G is subgroup of multiplicative group K star of a field K, and if -1 belongs to G, then we have to show mu G is 1, -1, sorry. Okay, so B part, G is subgroup of K star, where K is field. And we have seen in the classroom, I think it is not true, but we will assume that finite subgroup of K star, they are cyclic. So, and order of G is anyway finite, it is taken as universal hypothesis. So G is cyclic. Cyclic. Now what else is given? -1 also belongs to G. Can you say what is order of -1?
2.
This is 2. Now what you can say about order of group G? in the sense of it is even or odd.
Uh, it can be anything, right?
Uh, it has an element of order 2. Now what?
So it has to be of odd order. Is that
Odd
it?
order. What Lagrange theorem tells? Lagrange theorem tells what?
Okay, okay. I see. I see.
Lagrange theorem tells that any subgroup, order of the subgroup divides order of group. So what about this? Order of this subgroup divides order of G. That is 2 divides order of G. Right? So what should be order of G? Order of G is even. So because in the proof, actually in the proof it is given -1 to the power n by 2. Sorry, in the we have to prove this -1 to the power n by 2 into mu of 2g. Mu of 2g, this equal to -1. So that is why now we are very sure that n is even, so n by 2 is an integer. So no need to worry about anything else for if it is rational number or integer. Okay, this is integer. Okay,
Okay.
so what we have to show, claim is to show mu of g2, sorry, mu of g is -1. So mu of g is -1 from mu of g2. Yeah, mu of g is -1. Anyway, first in the A part, okay, wait a minute. What we have shown, mu of g is same as mu of g2, right?
Yes.
Okay, so it is good, it is enough to show mu of g2 is -1, correct? Now, what is
Yes.
g2 here? G2 is the collection of those g such that g square is 1. That is, this is nothing but zero set of this polynomial. This is nothing but v of v inside g of x square -1, right?
Yes.
So it is 2-degree polynomial. How many roots it can have in a field? At most 2.
At most two.
And g is subgroup of that multiplicative group. So it can order of this set g2. This implies order of g2 set. It cannot exceed 2. So this is less than or equal to 2, right? And since -1 belongs to G and 1 already belongs to G, so G2 is nothing but 1 and -1, right?
Yes.
Correct. Now from here it is clear. This implies that mu of G2 is 1 into -1 is equal to -1. Okay.
Yes.
So we have shown mu of G2 is -1. Sorry, here it was -1. Okay, so what next we have to show? That -1 is also equal to this. We have to show next claim is mu of 2g minus 1 to the power n by 2. This is also minus 1. Okay, so yeah, okay. Now what we can say about 2g? Mu of 2g, this is nothing but product of square elements, right? X square sorry, product of those GIs, sorry, which GIs are square of something, right? GJ square or something.
Yes.
And this is nothing, sorry, this is not equal to GJ square, J running from 1 to n, right? This is not necessarily equal in general. For example, if G is equal to this 1 minus 1, I minus I, then what is 2G? Square elements. Sorry, 1 is always square of 1. Minus 1 is also a square of I square, right? Minus 1 is minus 1 is I square.
Yes.
So minus 1 is also a square term, and I is not a square. Okay, from here it is clear. This is that. The 1 and minus 1 are only squares. So if you product here, mu of 2g will come minus 1, right? But if you product squares of all those elements from G, Gi squares, Gi belonging to G, this is nothing but 1 minus 1 square is also 1. Then I square comes, it is minus 1. And then minus I square comes, it is also minus 1. And it becomes plus 1. So if you take this product, this is large product, okay? And here we are only taking those elements which are square, actually squares. Okay, so we have to take care of that. So this is a small product, this part. Okay, so let it be written. This is rough idea. So this is nothing but Gi belonging to 2G. Okay, so how to do this problem? So what can we write here? Basically, Gi we can write here square. Gi square belonging to 2G and product of those Gi square. Okay, this is the by definition. Now
Why have we taken the square?
because G2 has this description. G2 is collection of squares. So that's why I'm writing this square. Nothing. G2, I just said G2 is nothing but x square, x belongs to G. Okay. So,
G2 or G?
sorry, 2G, 2G. Sorry, 2G.
But if
Right.
we are taking GI from 2G, then why do we have to square it? It will already be a square, right?
So, okay. So that was also correct. I was just writing so to not be being in confusion. So we can just write belonging Gi belonging to 2G and here Gi.
Yes.
Okay. So as a element, okay, let me change my color. Here it can be written, same thing can be written. product of gi squares belonging to 2g.
Okay.
So no confusion till now. Okay. So from here, what we can see. Okay, I'm thinking. Wait a minute. You can also think if you guess, it will be fine.
Yes.
So it depends on n. So n is even,
Yes.
uh,
Should
and
we
we can
also
say
make a distinction here? Elements belonging to G2 and elements which do not belong to G2 that way.
g2 or 2g. So if you see, 2g is also subgroup, right?
Yes.
So it is in fact a group. For any group, we have just seen that mu of g is same as mu of g2 from part A, right?
Yes.
And this implies mu of 2g, this group, is same as mu of 2g 2, right?
Yes.
Okay, nice. So if you use this, then what you get here, mu of g2 is nothing but product of gi squares, and gi square belonging to 2g when and now you are adding this extra condition so that element square is 1, that is gi square is 1,
Yes.
right? So now what is written here is this: those element of gi's, we are taking product of those element of gi squares, uh, such that, okay, gi power 4 is 1 and gi square, that we don't need to write, or we
It's
have to
going to
write,
be minus
we should
1
write,
or
we
1.
should write with these two conditions. But in g, or in fact in k star, what is how large is this product? There are nothing but x power 4 minus 1, because only these kind of gi's which satisfies this polynomial will be taking part inside this product, right?
Yes.
So this product can go as large as 4. That's all. So, but if you see, this is nothing but zero set of these two unions, x square plus 1 and x square minus 1. But it can happen that in your field, there are no solution of x square plus 1, for example, in real numbers, right? Then this
Yes.
product is means GI satisfying this condition will be at 2 only. 1 and minus 1 will satisfy that, right? But
Yes.
it can happen that your G contains all these 4 elements, something like 1 minus 1 and I minus I. Then all 4 elements will satisfy this condition, right? So we can take,
Can we use the fact that G is cyclic?
okay, if G is cyclic, then what?
Then 1 is the only element which is 1, and all the other elements which have raised to 4 is 1, then G square is going to be, Gi square is going to be minus 1.
Yes. So all this, if, okay, you can tell me once more. I forgot what you said.
That if Gi is equal to 1, then that is one case, Gi is 1, and the other case is Gi is not equal to 1, but Gi raised to 4 is 1 will imply that Gi square is minus 1, right?
No, no, it is not necessarily. For example, Gi power 4 is 1 or minus 1 also. But minus 1 to the power 2, if you take, it will be minus 1. Sorry,
Yeah,
it will be
right.
plus 1. So that is not the case. But however, we are almost understood the problem. This product is not uh, as large as we were thinking. So, so it so okay, we can take these two cases. So first case, when x square plus 1 has no solution. Nonetheless, this polynomial has solution, right? 1 and minus 1 is already inside G. Oh, sorry. But minus 1 might not be square of anything. It should be square of something, right? So case 1, we can take this has solution inside. Okay, so okay, okay, this order of this set x square minus 2, sorry, minus 1, this is 2 because minus 1 also belongs to G. But we are not sure if this has solution. So corresponding to minus 1, which is inside G, which satisfies this first condition, we'll take square of this. So we will take two cases. Case 1 is when all four roots of x power 4 minus 1 belongs to G. Then we can write this Vg x power 4 minus 1 as 1 minus 1, and I'm not without loss of generality, I'm just writing I minus I, or we can write something next other thing. Let's say y and y prime. Okay. The only condition they satisfy that x power 4 is equal to 1. Okay. Then we have to take squares of these things. What will be 2g? Okay, what will be this product? This product will be nothing but, sorry, only 4 terms in the product, and we have to take squares of them. Okay, so it is 1 square into minus 1 square into y square into y prime square, and this is nothing but 1 into, this also becomes 1, and this is, and what y square becomes. Note that 1 and minus 1 are roots of this, right?
Yes.
Hello.
Yes, yes.
So y and y prime should be root of this, correct? So what
Yes.
y square becomes minus 1. Y prime square also becomes minus 1. Is this clear?
Yes.
Okay. So what it becomes is, in the case 1, we are calculating only this part. Mu of 2g. Case 1, mu of 2g becomes 1. Also, note that order of y, what is order of y? 4. Correct?
Yes.
Because y square is minus 1 and y to the power 4 only becomes 1. And by Lagrange theorem, 4 divides order of g. Right? Means 4 into some k is equal to n. Now, if you don't follow any step, you can tell me. So now n by 2 is just some 2 into k, which is just even.
Yes.
In that case, what minus 1 to the power n by 2 becomes?
One.
This becomes 1. Is there any mistake? Because we have to show minus 1 to the power n by 2 into mu of 2g equal to minus.
Is it coming out to be just one?
Yes, it seems. Don't you see?
Because I also tried it using another way.
Yeah.
I took the generator of the cyclic group to be A, and the elements whose power raised to n is going 4 is going to be 1 are A raised to n by 4, A raised to 2n by 4, A raised to 3n by 4, and A raised to 4n by 4. And if I take
Okay.
the product of the square of these elements, I am also getting A raised to 5n, which is 1.
A raised to 5, but minus
If I
1 to the power n by 2, that is
if I
also
square them and add them,
okay. Wait a minute. A to the power n by 4, a to the power 2n by 4, right? A to the,
4n by 4, which is a to the power n. And then we
Yes.
have to square them and add product, take the product, right?
If you square them, what it will become? 2n, sorry, n by 2 plus, this will become just n plus 3n by 2 plus a to the power 2n, right?
Yes.
So n by 3n by 2, n by 2 becomes 2n, and this is 3n. Total is 5 of a power 5n.
Which is going to be 1 because,
A to the power n is 1, right?
yes.
And this is just 1. Now, yeah, there is a little mistake, I think. Minus n to the power n by 2, this also becomes 1 because n is even, right?
Yes.
Sorry, n is divisible by 4.
Divisible by 4, yes.
So, okay, we will see. What about other case when n is not divisible by 4? Then in that case, this part does not have any root, and Vg is nothing but Vg of x square x power 4 minus 1. This has order case 2. This order is 2. Then n by 2 is odd, right? When 4 does not divide, that is 4 does not divide. When 4 divides, and all 4 roots we will get. These are all 4 roots. This was nothing but case 1 is when 4 divides n. So n by 2 is odd. Then in this case, minus 1 to the power n by 2. This is nothing but minus 1. And what will be this? Okay, yeah, I understood. This is what I was talking about when I was starting this problem. I will come to that. We are doing some mistake, okay? So here, what is
Okay.
2g here? What is 2g? Because this
Squares.
has only roots 1 and minus 1. V of x power 4 minus 1. In the second case, this is just, sorry, this is just 1 and minus 1, which is lying in G. Not all 4 elements exist in the second case. So what will be 2G?
Just
Intersected with,
1.
okay, in what, with this extra condition, x square plus 4 intersected with what appears in the product, that only matters. I should write explicitly. We want this red shaded area, this part. So in this, we are taking all those GIs whose power is 4. So only focusing on those element GIs, their power is 4. So in this case, what squares of them becomes, this is nothing but 1, it's singleton 1, right? So product mu of 2G, this becomes minus just one element. With this extra condition, we can write it like, okay, let me write star. This denotes that Gi's power 4 is 1 and Gi square belongs to 2G. That is, Gi is a square of something. Okay, so this is in the sense of a star. Okay, 2G can have a lot of elements, but this, because of this condition, minus 1 and plus 1, these are only 2 elements. which satisfy x power 4 minus 1 is equal to 0. So that is why with this condition, star 2g is nothing but just 1, and we are getting mu of 2g 1, and hence that minus 1 to the power n by 2 into mu 2g, this is minus 1 into 1, so minus 1. Okay, now coming to here, what we were doing mistake is this. We have 4 elements, 1, minus 1, y, and y prime inside G, and with extra condition that they are the root of x power 4 minus 1. Now, which of them are square? What is 2G with this star condition? In this case, this is nothing but 1 and minus 1. We should not take these terms,
Yes.
right? So we just get plus 1 here on. Plus 1 or minus 1?
We are taking
No,
the squares, right?
we already taking a square. Now we should take product. So this is minus 1. So this is wrong, this part. This is fine. So in the second case also we get minus 1 to the power n by 2 mu 2g is equal to 1 into minus 1. Okay. Why we should not take square here? Because we already taken squares here. We already taking in the index notation, if you see, we are taking only g squares.
Yes, I get it.
So we should take product of these elements, which are coming from 2g. Okay, so I hope you understand. If you not, you can come back again.
No, I got
Let's see
it.
next.
I got it.
Got it. Okay. So we have to deduce that Wilson theorem, and then we'll see next part. What is Wilson theorem? P minus 1 factorial is congruent to minus 1 mod p. Wilson theorem. So if you want to apply part B, then what should be your field K and that K star? What will be the, what we should take that G, which is subset of K star? Any guess?
Take ZP minus 0.
Yeah. So K is equal to ZP. So K star is equal to ZP star, and we can take G itself. This is your G. Then G is finite cyclic group. Now we somehow want P minus 1 factorial is equal to minus 1 mod P. So any calculation here is just mod P. So what we have shown from part B or part 1? Part A. Sorry, part B. Mu of G is 1 minus 1. Sorry. Mu of G is minus 1. What is mu of G? Product of all the elements. What is elements of ZP star? 1, 2, P minus 1 bar. Right? So
Yes,
mu of G is
it will follow directly.
what?
It follows directly, right? The
Correct.
product is going to be.
The product is nothing but P minus 1 factorial in the bar, and on the other hand you have minus 1, and inside ZP. So this can be written as P minus 1 factorial congruent to minus 1 mod P. Okay, so this is direct proof. So we got Wilson theorem. Now we have extra thing in the part C. Other than Wilson theorem, we have to show when P is not prime of order prime 2, P is not 2, then minus 1 is a square in ZP. If and only if P is congruent to 1 mod 4. So B12, we have P is not 2, it is given, and we have to show that minus 1 is square of something in ZP if and only if P is congruent to 1 mod 4. So one side should be easy. Which side should be easy?
If P is congruent to 1 mod 4.
Okay, so let's do this. When P is congruent to 1 mod 4, then P minus 1 is divisible by 4, which is just 4 into some k. So x square is equal to minus 1 or some x in ZP. Now we have to check P congruent to 1 mod 4. This implies this part is trivial, right? This part is more trivial. X power 4 is equal to 1 or some x in ZP. This implies there exists x in ZP star of order 4. Correct? This implies Lagrange theorem. 4 divides P minus 1. And this is nothing but P is congruent to 1 mod 4. Not all the steps are if and only if, right? 4 divides P minus 1. This doesn't imply that there exists 4 other elements. Cauchy theorem tells if you have prime, right? Then you can have that element of that prime order. But is this true? 4 divides order of a group, then there is a 4 order element. Not right? This is not true anyway. So, so this
Can
is
I
only
suggest something in the above, the elements before P minus 1 by 2? Can we write them in terms of P plus 1 by 2? Like, and if there is some relation between P minus 1 by 2 and P plus 1 by 2?
the difference is 1. That's all I see. Here G is a non-trivial group, and we have to show the following are equivalent. There is a proper subgroup of G which contains all other subgroups of G. So means there are also proper, all other proper. In that case, G is finite cyclic group of prime power order. Okay, and in that case, G is finite, and SG, which is subgroups of G, is totally ordered with respect to natural inclusion. Now, let's see.
Do we need to use Silo's theorem here?
I don't think so.
Okay.
First of all, this part is easy, right? 2 implies 3.
Yes.
Because cyclic group have unique subgroup of given order. And for
Yes.
every divisor D of order of G, there exists unique subgroup of that order. And we have this chain. Let's say we have finite cyclic group of prime power order Z P to the power R. Then we have this subgroup Z P to the power R minus 1. Then we have, and so on. Lastly, we have Z P, and then we have trivial 0. So this is totally ordered, and G is still finite, and subgroups. These are only subgroups. Use Lagrange theorem or use that cyclic group have
Because a unique subgroup of
given order. Yes. Okay, so using that, this part is easy. Now, if what about 3 implies 1? First of all, any cyclic group of given prime power order is isomorphic to this. Okay. Then we can classify them. Okay, 3 implies 1. What should we do here?
we should take the maximum element of this totally ordered set of subgroups of G.
Correct. We take here in the they were above case just p power r minus 1, and then this contains all other subgroups of proper order, right?
Yes.
No need to write anything. What about 1 implies 2? This for example, for time being, we can assume G has order infinite. What will happen if order of G is equal to infinite? Then one fails. Correct? Hypothesis is one fails. For example, if G is Z, 2Z does not contain any other PZ. Any MZ does not contain NZ or GCD of MN is equal to. So we have to take So order of G's would be finite. Okay, one fails. How to prove this one fails? Let H be proper subgroup of G, which contains all other subgroups, which contains all other subgroup. Then, because this is proper, take an element A from G, but not from H. And what will happen to this cyclic subgroup generated by A? Because this is not contained in H, what it should be?
The entire set G.
Correct. This would be G. Now, once G is cyclic, G should be Z, and inside Z it fails. H will be of this form, some MZ,
Yes.
but it does not contain all other subgroups. All other subgroups are also NZ type. This implies G is isomorphic to Z, and in Z, this is contradiction, because in Z, uh, hypothesis fails. I should not write contradiction, but when G is isomorphic to Z, this is one fails from here. Okay, so order of G should be finite. Now, what about if order of G is some, let's say, order of G is this, P1 to the power M1, product of these things, PR to the power MR. Same thing we have to solve. Does there exist a proper subgroup which contains all other subgroup? Let again K be the proper subgroup of G, which contains all other subgroups. Then, because K is not equal to G, pick again G out from K, element from G, not from K. Then what will happen to cyclic subgroup generated by A? This will be contained in G,
Yes.
but this will be equal to G, right?
Yes.
Nice. So now once G is cyclic and G has this much order, so there exist elements of, okay, let me write it like this. A power P1 to the power M1. Order of this, what is order of this? P to the power M2 and so on, PR to the power M, right?
Yes.
And what about order of A to the power P2 to the power M2 and so on, PR to the power MR? This will be P1 to the power M1, right? Okay, now we come to use that A to the power P1 to the power M1. Order of this is P1, P to the power M2 and so on, PR to the power MR. This is less than So cyclic subgroup generated by a to the power p1 m1, this would be subgroup of K, because all proper subgroups are contained in K.
Yes.
Also note that a to the power p2 m2 and so on pr mr, this order is just p1 power m1, and this is also less than, and this implies a to the power p2 m2 pr mr. Cyclic subgroup generated by K is also contained in K. No, because K is subgroup, multiplication of these two elements, a to the power p1 to the power m1, this belongs to K, into a to the power p2. No, not this. What you can say about these two numbers? This number and this number. They are prime, right? Co-prime.
Yes.
We have
The
written
elements
such.
are inverses of each other.
What?
Are the elements
They
inverses of each other?
are the inverses of each other. Yes. I think product of these two things is becoming one. Yes, they are inverses of each other. Basically, they generate same subgroup. But anyway, from
Yes.
here you can conclude this, that because GCD of P1 M1, sorry, P2 M2, P3 M3, PR MR, this GCD is 1. This implies there exists X and Y inside Z such that P1 M1 into X plus P2 M2 is equal to 1. Correct? Now, if you power a power 1, this is nothing but a to the power P1 M1 into X into a to the power P2 M2 PR MR into Y. Because this a to the power P1 M1, this also belongs to K. A to the power from here is P2 M2 PR MR. This also belongs to K. Where this product belongs?
In K.
Belongs to K, right? Once A belongs to K, this implies K is equal to G. Now this is our contradiction. If we have more primes, there is problem, right?
Yes.
So we are in good situation that this kind of different primes cannot occur in order of G. So now what will happen when, so only case left is order of G can be, it should be, because in the other case we are getting contradictions. So the only case left is, or yeah, it should be, not can be. Order of G is prime power. Okay, here we conclude our theorem. You understood?
Yes, I got it.
Okay, so we can go to next question, part B. When P is a prime number and G is finite P group, that is the order of P is P to the power M from M. Then so that G has only one subgroup H naught of index P and use part A. This is trivial. 4.2 B. Given Order of G is just prime power. From first equivalence, when this finite cyclic of prime power order, is it clear or not?
Does it
It
have to
seems
be cyclic?
it should be finite cyclic, then only it will we can apply that. This is already finite given, and we have, is this cyclic? If we want to apply first part, then we have to take cyclic also, right?
Yes.
Otherwise it is not true. You are correct. So here we should take finite P group, finite cyclic P group. Then we can use above equivalence to show that there is single largest subgroup and these cyclic. Otherwise we'll get contradiction. You can use this when G is, let's say, ZP cross ZP cross ZP R times. Then there is not unique, it's not. Anyway, when G is cyclic, then from part A, there exists unique K of G such that K contains all subgroups. All other subgroups proper. Then what is index of K? G mod K. This is just P only, right? Because
Yes.
it is proper,
Yes.
and this should divide P power R. So only one, and after one we should get P. Okay. So when G is large, sorry, K is largest subgroup, so order of K should be just P to the power R minus 1. Order of G is anyway P to the power R. And there is no subgroup between G and K. K is the largest subgroup, okay? Then G mod K is P.
Yes.
Okay, so part B is also clear. Now we come to, we still have time. So we were coming to next question. AB commutative ring so that if every principal non-unit ideal A is prime ideal, A is field. If you can give some idea, we will solve it together.
We can
Okay.
take an element X and take the ideal generated by X.
Nice. Starting with it is fine, but remember that 0 is also an ideal, right?
Yes, so non-zero element.
Non-unit ideal. This implies 0 is prime by the hypothesis. What it implies? A is
Integral domain.
yes, at least we have shown that A is integral domain. Now if we want to show that A is field, we should take some non-zero element and we should get inverse of that element. That is the simplest trick. So okay, x non-zero in A we have taken. Now you are saying that consider ideal generated by this, and this is prime.
So we assume that the ring has one, right, identity.
Ring has one. Yes, ring always have one in our course. Will x square be 0?
No, because it's an integral domain.
Nice. So x square is not 0. What about this ideal? Right?
Yes, yes, yes.
Every principal non-unit ideal is in A, and we are also taken x non-unit. If x is unit, we don't have to prove. Let x inverse does not exist. That is A. X is non-unit. We are picking x non-unit. Okay. Otherwise, this ideal x square and all of this will whole become A, and that we don't want. Now we'll get some contradiction. If such a x inverse does not exist for an element, we'll get some contradiction. What about what is the relation between these two prime ideals, x square and x?
One is contained in the other.
Which one? This one?
One is contained the other way.
Right. So this is contained in here. This implies x square belongs to ideal general bias. Right?
Yes.
So we get a relation x square is equal to alpha into x for some alpha belonging to A. Correct?
Yes.
We will get we will have two cases from here. First case, when alpha is unit, what will have x square minus alpha x is equal to 0, and this will imply because x is not 0, it will become x is equal to alpha. This implies x is unit. Contradiction. Because we had taken x non-unit. Right?
Yes.
Now coming to case 2, when alpha is non-unit, we'll get some contradiction again.
X will
Then
not be prime.
what?
X square will not be a prime element, so it can't generate a prime ideal, right?
How?
Because it will be, it will, it is going to be not irreducible, right? Because it has a non-unit divisor, so it is generating a prime ideal, something in that.
I don't understand clearly. You can explain once more if you wish. I don't understand completely what you said. When when alpha is non-unit, what you can say from here? x square is prime, and x square divides alpha into x.
Yes, yes. I
X
get.
square divides alpha, or x square divides x. Right?
Yes.
From here, what you get, x square is equal to x square into k is equal to alpha, or x square into k prime is equal to x. Now, from the first, what you get from the first? X square into k is equal to alpha. Put this alpha in above equation, where we have x square. Let me write it as star. Some equation, maybe just a star. This becomes x square is equal to, in place of alpha, I'm replacing by x square k. And here we have x. And from here, what we have?
X square
This,
k
this
minus x will and
can we replace this again from star? So this implies x square is equal to alpha. In place of x, we are replacing x square into k prime. Now from here, you have this implies there is some logical error or not.
because if we take it on the other side, it will imply that kx minus 1 is equal to 0, since x square is not 0. Therefore, x is a unit, and even for this one, I think alpha into k dash will be equal to 1. So alpha is also not unit. So this is a contradiction.
In this step, everything correct, right? From here to here. No, right? We are just putting whatever we get, value of alpha and value of x. There is no error.
Yes.
Okay, but this is also wrong, and this is also wrong. So in a or statement, when both are wrong, then only we get wrong. So this is the oral contradiction here. So we get that x is no such x inverse, no such x exists. So for every x inverse exists. So this hypothesis is wrong, means for every non-zero element, x inverse exists. So for every x non-zero in A, x inverse exists. A is filled. Okay, what is second part of this question? M and B two non-zero natural numbers. Suppose M divides N, so that canonical group homomorphism Zn star to Zn star is surjective. You know, canonical map is anyway surjective. When we don't apply a star, just Zm to No, Zn to Zm. Yeah. Okay, let me write next one. 4.4. B. M divides N. That is anyway, M is less than M. What about this map? Zn to Zm. Canonical map.
Is
You know
it the
what
map
canonical?
A bar A modulo N goes to A modulo M? Is that it?
Is A bar modulo M.
Okay.
This map. This is well defined map because M divides N. For example, but anyway, this is always defined when you just take modem from a. This is anyway well defined map, but this is subjective. When M divides N. Right?
Yes.
Nice. So this map is well defined and it is subjective, but now we have to restrict this map in units. So we get a map after restriction, and that map is also well defined. Unit goes to unit. This is ring homomorphism. This is clear. I is ring homomorphism. Assume that mn is bigger than 2. Okay, so this is a ring homomorphism. So unit goes to unit, right? Are you clear with that?
Yes, yes.
Nice. So we unit phi of units, subset of units of Z. So it restricts I'm also writing restriction map as phi Z n star to Z m star. We have to, so this is surjective. So if Z is okay, if n is, let's say, p1 to the power m1 again into pr to the power mr, then Zn can be written as product of these rings p1 m1 cross zp2 m2 cross and so on. Okay,
Yes.
pr to the power mr. Okay, so this is from Chinese remainder theorem.
We can also say that the multiplicative groups also are isomorphic, right? Zn
Yes,
cross.
yes, yes. So from here, and if you have product of rings, when an element is unit, let's say R and S, you take units of this. What are those? These are R comma S, such that R belongs to R star and S belongs to S star. Right? Natural map,
Yes.
component wise multiplication. So this is R star cross star. So this map phi restricts to and showing this is surjective, we can show this component wise surjection. Okay, this natural map. So if n is of this form, n is this, then m is of this form, p1 to the power before k1, p to the power, sorry, pr to the power kr, where ki is just less than or equal to bigger than or equal to 0, less than or equal to mr, right? Because m divides n.
Yes.
Then natural map this phi, if we show component wise surjection, let's say from zp I to the power mi to enough to show star I to the power ki. This is surjective. Use this box description. If you show component wise surjective on units, then any unit of this product ring will come to the will be coming from some unit of the. Actually, here it is isomorphism, but I'm showing this morphism. So we have this is surjection on components. This is map from phi is just map from z p1 to the power m1 star cross z pr to the power mr star to z p1 to the power k1 star. This is also cross means component wise. This becomes component wise, that you have to notice pr to the power kr star.
Okay, I get it.
So it is enough to show that component wise in any ring you have one, so they are non-empty at least. So this, if you show this surjective, so it will be surjective.
In
Okay,
phi,
so
that should
showing this,
be pi raised to ki star, right? Z.
yes, sorry. Now how to show that? Take any unit of z, let x belongs to z star of pi ki. What is property of this x?
X is a unit.
Let's say this is x bar, when then x will be prime with pi to the power ki, co-prime.
Yes.
Nice. Now this implies x with p to the power pi to the power mi is also co-prime.
Yes.
This implies x bar is unit in z pi to the power mi, which goes to x bar, which goes to x bar. I should write x bar. This x is special bar. Okay. goes to X bar belonging to Z mod P I to the power Ki by canonical map. So actually we don't need to go to these projections. We don't require to be we can just use same thing up here. We don't need to do anything this much calculation. So can I delete it?
Yes, yes.
So I'm just deleting all of these things. What are units of ZNs that you know? So if X
Relatively
belongs to
prime.
ZM star, then X, let's say X bar here, X with M is GCDs. Oh, I think we required that. With M, it is GCD is getting 1, but that doesn't mean that
Yes, for primes we can say that. Okay.
for primes we can say that, yes. So X goes to P by a canonical map. So phi I is I is subject to. Okay, so this is done. But if such a K exists, taking any element outside K, we are getting G cyclic. That is also nice. Now we have shown that order of G is finite and G is cyclic. Because such a K which contains all other subgroups exists using that only. Now we have to show only one prime appears. So once G is cyclic of order given, let's say this is your N, G is isomorphic to Zn.